Hello and good evening, everyone. Welcome to my YouTube channel. Hope you guys are doing well. Today, we'll be discussing the topic unlocking colors from pixels to palettes. So, we'll be talking about color spaces and color quantization. So, the flow which we'll be carrying is we'll be talking about firstly color spaces and how we can represent colors. And we'll end our discussion with color quantization. We will be talking about two methods of color quantization. So that will be for today's lecture. And so in this lecture, we'll be talking about basically pictures and like colors. So when we talk about pictures, what is the most beautiful part of a picture or what gives beauty to a picture? That is colors. So like we'll be representing how a computer interprets colors and how different it is from our interpretation of colors. So our goal will be to learn these two topics today. So we'll start from the very first topic, which is like foundation of colors. So what when we talk about colors or a picture, what is the like thing which comes into our mind? We can say like, what is the building block of a color? We can, or a picture. What is the building block of a picture? We may say it is a pixel. You might have heard about this term, like when we are looking for phones, we may say we might have heard of this term called pixels, like 16 megapixel phone, 64 megapixel phone. So from our very basic understanding or layman understanding, you can say more pixels a picture might have, more clear it will be. So let's talk about image as a grid. So image as a grid, it it will have like image is a massive grid of many small pixels. So that is our first line. A digital image is just a massive grid of many tiny squares called pixels. So more pixels it will have, we can say more clear our picture will be. So each pixel is numbered from 0 to each pixel has three colors, is formed out of three colors, and it has like three each number has a color from 0 what each color has a number from 0 to 255, which represents its mm, depth, or we can say brightness of that particular color. So each component uses a 8 bit of data, meaning its intensity is from 0 to 255. So if we use three colors and each numbering from 255, we can create 16.7 million possible colors. These are known as 24-bit true colors. So we can say each color is formed out of three main colors, which is RGB, red, green, and blue. So now let's look at the geometry of this model. So this is our model for RGB, which is R, G, and B. So here we can see that combining all the three colors, we can form a white color. And here it's this image basically shows the additivity of these three colors. So if we combine red and green, we'll form a yellow, and green and blue will form a cyan, and blue and red will form a magenta color. So in this way, we can create like all the colors from using these three basic colors. Let's, but let's look at the limitations of RGB. For example, if um, we talk about colors, but for example, if there's an artist or if we are painting something, for example, I'm using the color orange or green. So if I tell someone who is painting that I need a slightly darker version of green or a lighter version of green, he knows what he has to do. He might mix it with the different colors to form little bit more darker version of green, or if he might dilute the color to form a lighter version of green. But then if we talk to a computer and tell a computer, "Ki, I need a slightly lighter or a darker version of orange," the computer has to change all the three values of R, G, and B so as to attain a lighter version of it. So RGB is great for hardwares, but it is like difficult for analysis purposes. RGB is great for representation, but analysis, RGB cannot do that. RGB can do that, but then editing and analysis can be done much better using a different model, which will introduce as HSV. So it is RGB is unintuitive for humans. As we said, if we have to make darker or lighter, it's easy. But for image analysis and editing, we can create a much better model, which is HSV. HSV uses three parameters, which is hue, saturation, and value. Hue is like hue is basically the color or the name of the color. So it's like if we have a circle and we arrange colors in a circle, if we might if you might have used different paint applications, we might have seen in a circle we can see different colors. Saturation is basically the purity or vividness. For example, if we say if we have a less saturated image, that means it is a dull image. And if we have a highly saturated image, it is a vivid image. Value is basically the brightness of that image. If we have a light image or a brighter image. So this model basically we can represent it in a cylinder. So if we see this, we see a cylindrical representation in which hue, if we say we have different colors, as you see, we have a cyan color here, and if we see a darker blue color here, then we move on to pink, then we move on to red, and then finally we have yellow and green. So we in this way we can in a circle we can represent many colors, and then if we see saturation, it is like we have a dull color here or basically a grayish version of that color, and then a more brighter, and value is basically the brightness, which if we see the to the lower end of the cylinder, here is a very dark color, and if we go up we can see a lighter color, sorry, brighter color. So this is our HSV visualization or HSV representation of colors. Next, we are done with the color spaces theory, and next we'll move on to color quantization. So, why do we need color quantization? So, firstly, what is color quantization? So, I'll give you an example. If we have, if we are given an image, and if we are given, we can say 200 or 300 colors, and if we are said these are the different colors used in this image, and now you have to recreate the same image if with maybe 20 different colors or 16 different colors, so that would be difficult if we choose the wrong colors or wrong combination of colors. So it is basically the process that reduces the number of distinct colors used in an image. So it's like basically we can say this is like a compression method or using less number of resources. So we if we talk about the color quantization methods, we might need to look at what do we say? We might need to look at the methods which we use best resource allocation. We are supposed to do a task in the best of our ability with less number of resources. So we need a better model for that. So to represent an original color using a much smaller palette. For example, generally we have, as we said, 16.7 million different colors. But now we cannot use 16.7 million because some older formats might not allow us to use all those colors. For example, very common, it is a GIF format. We are not allowed to use so many colors. We are supposed to use less number of colors. Older screens and hardwares, they have limited number of colors. So now we'll be looking at color quantization methods. So if we see first method is uniform quantization. So if we look at this image, as I said, this same image or a similar image, this is a most common example is our sunset. So sunset, if you look at near the sun, it is like an orange yellowish color, but then this end we see a darker color, which is like black and blue. So since in this part of the image, right side of the image, we can use maybe 16.7 or we can let's say many colors we can use, so we can see that coming from a darker version to this orange color we can create the transition in so many steps, maybe like millions of steps. But then in this format we see even if you look at these mountains, there's a difference. So and in this format we see we made that same transition we made here which was in a million steps, maybe we made this transition in like 20 to 30 steps. So that is basically our color quantization. We are using less number of colors. Even if we look at the sun is not as clear as it is in the writer side. We see it is like much like we see edges in these parts of the image, but we don't see such distinct edges in the right side. It's because we are not supposed to use so many colors. We are using making the sun using only three or maybe four colors. That's why these steps we see. And same as in the mountains, we only use like three colors here, but at the same time here we see mountains are lighter on this upper side and lower these are darker. So this is basically color quantization. So let's talk about our first method, which is basically a bad method, which is uniform quantization. So it's like if we are drawing something, if we are making a landscape, let's say we are talking about grasses, green mountains, or basically the image which has one particular color. So what uniform quantization does is it divides the 0 to 255 range into equally sized blocks. So uh, basically, if we have 255 blocks, it might divide the same thing into like four blocks, eight blocks. So the problem with that is if we are making something like a landscape, which is mostly of green color, but then we are using maybe blue color, pink color, which is not in this landscape. So this method is not efficient because it uses colors which are basically not in that image, and we don't need those images. So this method is like waste of space, we can say, or waste of resources because we are allowed to use only limited amount of resources. So it's this example is given to reduce 256 shades of red to four shades. We might use 0, 85, 170, and 255. So this approach ignores how colors are distributed in the actual image, because since we are using all the colors which we have and giving each color equal priority, and some of the colors might actually not be needed in our image. So it leads to visible color transition known as color banding. As we saw in our previous example, this is like a color banding. We see different rings, which basically makes our image looks ugly, and basically the beauty of that image is lost. It is not appealing to the human eye. But this next method, which we'll be talking about, that will create much beautiful and we can say much perfect images. So this was our simple rounding method or uniform quantization. Next method is k-means clustering. So what this method basically does is it firstly it creates a like 3D space of colors. So instead of X, Y, Z axis, we have axis representing RGB with 0 to 255 values. So this way we have a 3D space of colors, which is RG and B. And so in that 3D space, our goal is to find K best representative colors. So my K may be like any number given. So we'll form K clusters looking at our original image, and whatever best clusters are needed in that image. In that way, we'll be forming different clusters from our 3D matrix. And once we form that clusters of similar colors or clusters of colors in that image, we'll try to find the centroid of that cluster. Whatever clusters we have, we might have a certain centroid of our cluster. So we'll find the centroid of a cluster. That value will be using in our original image or to recreate the image. So our goal is to find k best representative colors. Means algorithm groups similar colors together. It forms a cluster. The average color of each cluster will become one of the k colors in the new palette. What is the average color? It is like a centroid. So it is a better representation. Why is it? Because if we take an example, if an image has 90% blue and 10% red, let's take maybe sunset example or maybe a sunrise example, because if we look at the sea, it will be much blue, and we can say we have a slightly yellow color because of our sun. So we can say that image will have 90% blue and maybe 10 or 20% of not red, we can say yellow. So what we'll do it if we are given a value of 16, if k is equal to 16, what it will do is 14 out of 16 values will be of bluish color and only maybe two might be of yellow color. Unlike our previous method, which is using all the colors which are absolutely not needed in our image. Maybe a red color, pink color, or any other color which is not required in that image, we are using. But in this method, we are using maybe 14 out of 16 blocks will be of blue and other two will be of yellow, which is much better method of representing. So what will happen in this case? It will create a much beautiful and much more accurate final image. So we look at this image, which is first we can see this is our original image, and second we can see this is our uniform quantization. So sorry, this is a K clustering image. This is a uniform quantization image. Uniform quantization, as you can see, there are again forming the same ugly rings, which are not needed and which makes our image look basically not appealing. And this is a K-means method, which makes our image, if we can see, there is like very slightly less number of rings, or we can say those are like almost invisible. So what is nearer to this original image? Obviously, our k-means method. This image is much more similar to this image, unlike this one. This doesn't look good, bad. So this is our original image. This is our k-means method. So what do we? We obviously say k-means is a better method. So we talked about image quantization. Uh, what are our applications? uh, let's talk let's talk about a very good example, which is our GTA Vice City game. If you guys might have played, if you notice in that game during sunset, we can see like different blocks or different shades of those sun, which are not clear. But unlike GTA Vice City or one of those older games, if we look at the newer version of game, maybe GTA 5 or 6 is coming, I hope. So if you look at those version of game, we'll see sunset images are much clearer and they are like more aesthetically pleasing. So, or any other game, let's say we'll simple that Nintendo games or Mario games, those we see that those games use very like limited colors, or like they don't use different color transitions. So those older version of games, they use image quantization, and that is like the application. And you can see image compression is or GIF format that obviously uses image quantization, because 16.7 million colors cannot be used in a GIF. And we can see feature extraction, posterization, artistic efforts, and video game graphics. As I said, video game graphics. And let's look at this feature extraction and artistic effects. Different artists use quantization to intentionally flatten color ranges, and quantization simplifies the color information, making it easier for visual algorithms. So yeah, basically to make calculation simple, all we can say, instead of using so many resources, let's if the same work can be done with lesser resources, it's good, right? So that was our image quantization basically. So next is our final summary. We talked about color spaces and color quantization and two different methods of color quantization. So yeah, this was it for today's discussion. I hope you guys had a good time, and yeah, please like, share, subscribe. Anything works. Thank you so much, guys. I hope you have a good day.